When an electric fan is connected to a 115 volt supply, it receives less voltage compared to a 230 volt supply. This lower voltage results in the fan motor running slower. The current drawn by the fan is inversely proportional to the voltage applied. This means that when the voltage is doubled from 115 volts to 230 volts, the current is effectively halved. Power consumption is calculated as voltage multiplied by current. Considering the voltage is doubled from 115 volts to 230 volts, and the current is halved, the overall power consumption remains the same. A kilowatt-hour meter measures the energy consumed over a period of time. It calculates energy by multiplying the power consumption by the amount of time the power is consumed. In the scenario where the voltage changes but the power consumption remains constant, the disk rotation of the kilowatt-hour meter will be similar for both 115 volts and 230 volts. This indicates that the energy consumption over time is the same regardless of the voltage difference. To reiterate, the fan runs slower at 115 volts because of the reduced voltage. However, the overall energy consumption remains the same as when the fan is operated at 230 volts, and this is because the current is halved at the higher voltage. This is the reason why the kilowatt-hour meter shows little to no difference in disk rotation for both voltages. It is important to understand the relationships between voltage, current, power, and energy consumption to grasp why this phenomenon occurs. The power consumption is the rate at which electrical energy is transferred by an electric circuit. The standard unit of power is the watt, equivalent to 1 joule per second. Electrical power is commonly produced by electric generators, but can also be supplied by sources such as electric batteries. Electrical power is an essential component of many appliances, machines, lighting, and heating. Electrical power is usually solved by the kilowatt-hour, which is a unit of energy equal to the amount of energy used by a 1 kilowatt device operating for 1 hour. Electrical energy is the energy that is derived from electric potential energy or kinetic energy. When loosely used, electrical energy refers to energy that has been converted from electric potential energy. This energy is supplied by the combination of electric current and electric potential that is delivered by an electrical circuit. This converted energy can be used to do work or generate heat. Energy is generally measured in joules, but in real-world applications, it is often more conveniently measured in kilowatt-hours. Voltage, also known as electric potential difference, electric pressure, or electric tension, is the difference in electric potential between 2 points, which is defined as the work needed per unit of charge to move a test charge between the 2 points. It is measured in volts. Voltage can represent either a source of energy, or lost, used, or stored energy. A voltmeter is used to measure the voltage of a circuit. Current is the rate of flow of electric charge past a point or region. Measured in amperes, it represents the amount of charge flowing per unit time. Electric current is what causes electrical components to function, powering everything from light bulbs to electric motors. The flow of electric current is controlled by the voltage and resistance in a circuit, as described by Ohm's law. Ohm's law states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points and inversely proportional to the resistance between them. Mathematically, it's expressed as voltage equals current times resistance. This means that if the voltage is doubled while the resistance remains constant, the current will also double. Conversely, if the resistance is doubled while the voltage remains constant, the current will be halved. In the case of the fan, the motor's internal resistance remains relatively constant. Therefore, when the voltage is doubled from 115 volts to 230 volts, the current would initially tend to double as well, according to Ohm's law. However, the fan's design and the way it interacts with the power supply ensure that the actual current drawn is halved when the voltage is doubled. This is done to maintain the same power consumption. Power is calculated as voltage times current. If both voltage and current double, the power consumption would quadruple. If both voltage and current halved, the power consumption would be a quarter of what it was. Because the power consumption is designed to remain the same, the current must be inversely proportional to the voltage. The fan's motor is designed to operate at a specific power level. When connected to a 115 volts supply, it draws a certain amount of current to achieve that power level. When connected to a 230 volts supply, the motor adjusts its current draw to maintain the same power level. This adjustment is achieved through the internal design of the motor and how it interacts with the power supply. The kilowatt-hour meter measures the energy consumed over time, which is calculated by multiplying the power consumption by the time the device is operating. If the power consumption remains constant, the energy consumed over a given period will also remain constant. That's why the kilowatt-hour meter shows no difference in disk rotation for both voltages. The disk rotation is directly related to the amount of energy being consumed. The fact that the fan runs slower at 115 volts is simply because it is receiving less voltage. The motor is not able to spin as fast with the lower voltage. However, the energy consumption remains the same because the motor is drawing more current to compensate for the lower voltage. In essence, the fan is doing the same amount of work, just at a slower pace when operating at 115 volts. This demonstrates the fundamental principles of electricity, including the relationships between voltage, current, power, and energy consumption. The design of electrical devices and power systems takes these principles into account to ensure that devices operate efficiently and safely. Firstly, it's essential to recognize that the speed of the fan motor is directly influenced by the applied voltage. At 115 volts, the motor receives a lower electrical potential compared to 230 volts. This reduced potential translates to a slow rotation speed of the motor. Secondly, the power consumption of the fan remains relatively constant regardless of the applied voltage. Power, measured in watts, is the product of voltage and current. While the voltage doubles from 115 volts to 230 volts, the current drawn by the fan is effectively halved. This inverse relationship ensures that the overall power consumption remains the same. Thirdly, the kilowatt-hour meter measures energy consumption over time. Energy is calculated by multiplying power by time. Since the power consumption of the fan is constant regardless of the applied voltage, the kilowatt-hour meter will register the same energy consumption for both 115 volts and 230 volts. The meter's disk rotation is proportional to the energy being consumed. The disk rotates at a speed that corresponds to the rate of energy usage. Because the energy consumption is the same for both voltages, the disk rotation remains constant. Therefore, the observation that the fan runs slower at 115 volts while the kilowatt-hour meter shows no change in disk rotation is a direct consequence of the interplay between voltage, current, power, and energy consumption. The fan's motor is designed to maintain a constant power output, and it achieves this by adjusting the current draw in response to changes in the applied voltage. When the voltage is lower, the current increases, and when the voltage is higher, the current decreases. This inverse relationship ensures that the power consumption remains constant, and as a result, the kilowatt-hour meter registers the same energy usage regardless of the voltage. In practical terms, this means that using the fan at 115 volts may result in a slower airflow, but it won't necessarily save energy. The fan will simply run for a longer period to achieve the same cooling effect. Conversely, using the fan at 230 volts will result in a faster airflow, but it won't consume more energy. The fan will run for a shorter period to achieve the same cooling effect. Understanding these concepts is essential for making informed decisions about energy usage. While it may seem counterintuitive that a device can run slower without saving energy, the explanation lies in the fundamental principles of electricity and the design of the device itself. The kilowatt-hour meter is designed to accurately measure energy consumption, and it does so by taking into account both the voltage and the current being used. By understanding how these factors interact, one can gain a clearer understanding of how energy is used in everyday life.